right, welcome to Friday. I think you'll have a better weekend ahead than I will. I will grade these exams. I have 3 other classes that were online. Exams finished on Thursday, so I'll be reviewing a lot. Some of you have contacted me, let me know you don't feel you did as well as you were hoping for or feeling. Here's the deal. They say we're not supposed to say this, but I'm going to say it. The coordinators, this is my first time teaching the class, so I'm kind of learning as I go through it how they work it. But they did tell us at the beginning that generally they start off with the strict grade breakdowns, but by the end they change that. So it's going to lower. So that's one thing that's different. The other thing is, as I go through, we'll work together. No matter how you did, we'll make it so you can keep progressing on. And the best way to make progress in this class is to move forward. The best way to understand that stuff from the first part is to move forward. And then it'll become clear as we go, because now we start focusing on really what does a derivative do for us. And then that's where it starts to make some sense. When we talk about limits and moving, it's so technical and we get something, but we don't know what we have. But now we're going to focus on what we have is a rate of change. We have our velocity, or a second derivative would be an acceleration. So we have something physical that's telling us about what's going on. Okay? And the techniques we have already started with 2.3 are the calculation to get what we need to get that derivative are going to be much easier than when we used limits. And today we started into sort of our first formula approach to kind of taking more complicated derivatives, or derivatives of a combination of things going on. So today we look at what's called the product rule, 2 things are being multiplied, and the quotient rule, 2 things are being divided. And we'll look at something called the chain rule on Monday, which is a function inside of a function. So we look at basically the rules we have already that, take the exponent down and multiply and then subtract 1 from the exponent. That's pretty much what we'll be doing, but we have to organize it in a way, and that's what these other rules are about. Okay. Since we're switching gears, I thought we'd change the picture a little bit. And a lot of times when we talk about derivatives, we talk about roller coasters, because roller coasters is where you get to feel the derivative, right? How many of you like rolling roller coasters? I used to, but I get sick on them. But those used to be my favorite thing. And you get to that top, right, and you just kind of feel weightless almost at the top. That's a 0 derivative. And then what happens after the top? Whoa, that's increasing derivative. That's you're picking up speed. And then you get to the bottom and you go up the other way. So you actually get to feel a derivative if you think about a roller coaster ride. Okay. So here's our new schedule going forward. So test 1 is behind us. Again, I will review those. I've got the stack all set up. I've got the key made up. They're ready to start looking at. I was just too tired from Thursday's meetings and everything, but I will get on it first thing when I get back home tonight. And I got to get it all done by Sunday night before I go to sleep. But where we're at is 2.4. From the previous setups, I've learned a little bit. The due dates for everything we've got going for 2.4 to 2.8, and I might move 2.8, but they're down here when we get to the review. So that's the goal, is to get it all done by then. But if you can keep on track with it as best as possible, that's good. Now, if there's 1 or 2 that's a struggle, or a few that are a struggle, that's okay. But at least try those early ones so that you can kind of keep on top of things. Some of the examples I put in the lecture I take from the homework, so keep moving on those. And then we have actually 2 kind of reviews. We'll have a chapter 3 review once we get through that part, and then we'll have an exam review where we put them together. So we've got a little bit more space in here before that next exam. And again, we've got things that are hopefully going to start clicking, because we're actually going to make applications of the derivative. We doing okay? Okay. Remember, it took me two times. It took me 2 times to get through calculus. Both first and second. I took them second time. But again, the second time around, it went so well because the professor was dyslexic, and I found out I'm dyslexic, and the way he taught melded with how I learned. But also, I had already taken it once, and so I kind of had it put things together. My goal is not that you go take it a second time, but that this will be, and if this is your second time, this is your last time through here, okay? But we'll do it. So a little bit of review from 2.3. Derivative of a constant is 0, remember, because that means it's y equals a constant is a horizontal line. It's got a slope of 0. Remember, put those two words together, derivative, slope, slope, derivative. That's what they are. Okay. Derivative is just a slope. It's a rate of change. The power rule, this is the major part that we're going to use. Take that exponent, multiply it in front, and then subtract 1 from the exponent. We also find if we've got a constant times a function, we can just sort of take it out front, get the derivative, and then multiply the derivative by that same constant. Okay, so these are just things we picked up in 2.3. Oh, I forgot. Well, at the end of 2.3, we picked up some trig derivatives. And again, we kind of looked at the graphs and what happened if we looked at the rates of change of those graphs. And we saw that the sine graph, its derivative is actually the cosine graph. Because if you look at the rates of change, it redraws the cosine. And the cosine is close, but it's actually the negative sine function. So that's the one thing we have to remember. Take the derivative of cosine, you get a negative sine. Okay. And then these guys were supposed to be first, but that's okay. We had a sum rule, so for adding 2. So this was really the first part. For adding 2 functions, we basically can just take the derivative of each of them and add the result. And the difference rule. They're subtracting, take the derivative of both and subtract them. Not bad. Today we're kind of going to build on that. We're going to take 2 functions that are being multiplied and see if there's a way we can take it directly without multiplying it out. Because sometimes the multiplying out is going to be a mess. A lot harder. So again, we look for easier ways to get at it. So we're going to develop the product rule by first taking the derivative of this. And so I'll see if you can do it on your own. You've got the background for it, right? Just turn by turn, take its derivative. And incidentally, when we talk about derivative, I like using what they call the prime function, so that's h prime. Can't remember if that was Newton's function or Leibniz, but there was a German guy and a British guy, and they used 2 different notations, and that's why throughout this you see 2 different ways of writing the derivative. This is the one I like, just a little prime. And so what is this going to be? 2 comes down in front, and then we subtract 1 from the exponent. So x, I'm going to put it there just to remind ourselves. I think that was helpful for me. It's not that it disappeared, it just became that. And then up here there is a 1. 1 times -7 is -7. Subtract 1, you get x to the 0. Anything to the 0 power is 1. Okay, so that's really 7 times 1, but we won't write it. And then how about this last part? 0. It's a constant, so it just disappears. Good. So that's what we get. What we're going to see now is, what if we looked at this, what if we factored it, okay, that's what's been done, and looked at it as 2 separate functions. Is there a way we could directly take its derivative? Now, in the past, when we were looking at it, so just FOIL it out and then take its derivative. That was the easier way, and I still agree that's the easier way. But what we're going to see is that there's also sort of a formula we can use to take this as 2 different pieces, put it back together, and we'll get the same answer. But that's going to help us with ones that are more complicated, that wouldn't be very much fun to multiply out. Okay? And I thought, well, let's but I don't want to confuse you, because if I try the wrong things and they don't work, then those are the things you're going to remember, right? So let's do it right the first time, and hopefully it makes sense. So I look at this first one as the function f, and the second one as a function g. And so think about, in this case, like when we FOIL something out, right? First, outer, inner, last. A lot of us like to leave off that middle term, because we just do the first and the last, and we think we're done sometimes. There's that middle term. That's sort of what happens here. So the formula we're going to get to is, if we want to take this whole derivative, is we're going to take just the first one as it is, and we're going to multiply it by the second one, the derivative of the second one. Okay, so I'm going to show you, we'll put those pieces together. And then we're going to take the second one just as it is, as the original function, and then we'll multiply it by the derivative of the first one. And we'll formalize this, but it ends up working, and we're going to show it works, and we're going to say, okay, why? If you want, in the text they use limits, our favorite, right? And they show a proof of it, but that wasn't very insightful for me. Just seeing that it works will be. And then we'll use it, and we'll say, okay, it always works. I don't, I get in trouble for this. I say, I don't care why, but it works, right? I don't care what makes my car run, or my motorcycle, whatever I'm on, it runs, okay? I do want it to keep running, but, okay. So what I do is I look at this, and so I kind of come over here and I make my different pieces. So here's the f function. Here's the derivative of the f function. Here's the g function. Here's the derivative of the g function. So I'm going to get these four pieces, and then I'm going to reassemble them into this little formula I have over here. Well, the easy part, what's the f function? It's just x minus 8. Now that I've got it out, it's by itself. What's the derivative of x minus 8? Good, 1. It's kind of, because it's x to the 1 power, the 1 comes down, 1 minus 1 is 0, it's just 1, the number 1, that's all it is. And you're going, well, how's this going to do anything? Well, it'll all work out. G function is the second one, x plus 1, so what's the derivative of g? 1. Nice and easy, right? Because that's x to the 1 power, bring the 1 down, subtract 1, you got x to the 0, so that's just 1. Now let's put it in, because what are we supposed to get? We're supposed to get this. And we will, if I didn't mess something up. But, okay, so I've got the f function, the first part that, nothing's been done to it. So that's x minus 8. I'm going to put a parentheses. And that gets multiplied by the g function. The derivative of g. And then I'm going to add the g function, which is x plus 1, times the derivative of the f function, which happens to be 1. So that gives us, we distribute through, we get x minus 8, the 1 going through, right? And on the second one, we get a plus x plus 1. We add these together, what do we get? 2x minus 7, which is what we got when we took the derivative in the old way from last week. Or Monday, or when, well, yeah, I think we did it last Friday. Does that make sense? It worked, okay? And it's always going to work. So when we've got, the thing is, we just have to realize when we have really two separate functions, because they don't announce it, here's two separate functions, but you're going to see things being multiplied. And then you recognize that, okay, I got to take the derivative of this, and the derivative of this, and the derivative of this times this one unchanged, the derivative of that one times this unchanged, and add them together. Now, you can do it in any order, right? Because we've got addition. Addition, it doesn't really matter if you do it the other way around. But we're going to kind of do the formal product rule, which says this. And again, they're using different notation. They're using, I think this is the German notation, but it might have been the British notation. It's, like I said, it's not the one I like. But it's just saying the derivative of two functions multiplied together is going to be the first function, nothing done to it, times the derivative of the second one. And so I'm going to write it out in the notation I kind of like. So this is, we'll just say it's f times g, get rid of the x's and everything. When we go to take its derivative, it's just going to be f, whatever it is, times the derivative of g, plus, notice it's g without anything done to it, just as it was, times the derivative of f. If you like to have kind of a catchy saying, you could also say it's f dg plus g df, and the d means derivative. Okay, you're going to see this. This might be helpful when we get to the quotient rule. So this one's usually not as hard to remember, but put a little rhythm behind it. Maybe it sticks better. F dg plus g df. So you get these rhythms. So it's a function with nothing done to it times the derivative of the other function with nothing done to it times the derivative of the other, and it works. It works. And again, if you're still curious about why does it work, look at the textbook. Come see me during office hours, and I'll listen to you talk about it, and I might be able to help. But it's honestly, I don't get into the proof parts of them. That's not my. In fact, I had to take a math proof class. Barely got through it, but I know what works, and that's how I go. Okay, so we okay so far? So let's look at an example. It's not announcing that these are two functions multiplied, but I see x squared times sine x. It's a little clearer because I know one's a trig function, one's a polynomial. So this one's not so bad. I can see, yeah, it's two. I can look at this as two different functions being multiplied, so I'm going to use the product rule. So I like to just go ahead and label things. And again, we don't have to do f and g, but whichever you want to stick with, give them some kind of a name. And, so the first and the second, whatever, f and g. And so again, I'm going to say, here's f prime, here's g prime. And again, I pull it off to the side and just make my pieces, and then I'm going to reassemble it. There's my pieces. If you try doing it all together, at least at the beginning, it can get very confusing. That's how I tried, but it didn't work. This is what my dyslexic professor taught me to do, and this is what works. First time it didn't work very well. Yeah. So f is, again, we'll call this is x squared, right? And it's just natural. I got x squared, so what's its derivative? 2x, right? The 2 comes down, subtract 1 from the exponent, 2x to the 1 power, or just 2x. Good. This is why I do this too. You got to take the derivative anyway, and this helps you focus on what you're doing. G is just sine x. And then you start also to, and I like to put parentheses around sine and cosine because it's really got an input, and when you don't, I don't like it. But the book does it a lot, so I mean, and if you don't like putting parentheses, that's fine. It's just sometimes as it gets bigger, you really need to. So it's later on. So what's the derivative of sine x? Cosine x. So see, that's the other reason is this, we're doing a lot of different things. We're pulling off a trig function thing, and that's probably stored in a different part of the brain than a polynomial. So you got to think about oh yeah, that is just cosine. Is it negative cosine? No, it's just cosine. The other one is, but that's where I would mess up. I might have to even look it up. In fact, I encourage you to maybe get one of these. I used to have these 4x6 cards that are, they're not just the little cards that are a little bit bigger. I would write all the stuff that you sort of have to memorize, because I'm actually not very good at memorizing, but at the same time, I've got like a photographic memory, which doesn't sound right, but if I just look at something, I remember it. If I try to remember it, I forget it. I don't know why that is, but I just carry that card around, and when I'm doing my homework, I set it down there. If I'm, I can't remember which one, I take a look. Eventually, I stop looking. Okay, so I encourage you to do that, even though, maybe you're not going to be able to use that card on the test, but you won't need to if you get used to sitting it down. That these are all the facts that I'm going to be using. Whenever you need to, you just glance at it. It's right there. You don't have to go filing through some papers. So just your important card, maybe 2 sides or a couple cards, whatever you need, but just kind of a nice little organized. These are the basic facts we're working with. So then what do? We do f dg plus g df. And so I pull my pieces. I get an x squared here. Dg is cosine of x. And then I get my g function, which is sine x. And then I get my df, which is 2x. And again, you could probably put the 2x in front of the sign, so make it pretty, whatever. Yeah, you could probably do factoring. You could probably, there might be some trig identities we can use later on. But I tell you what is this function we have right now? What is the purpose of the function we just got, the derivative? Thank you. Slope. It is slope. It is giving us a rate of change. It's perfectly usable. You give me an x point, I plug it in, I know what my rate of change is. That's what we're going to use it for. It's not for a beauty contest to try to make it look and simplified and all this stuff. Just use it as it is, right? That's my, and I think WebWorks will recognize mostly. So we don't, and like I said, I don't think there's much to do here, but we'll get to ones where there might be some simplification. I don't care about simple. I like leaving them, to me, this is a simple form. Okay. So far, so good? Again, nothing new as far as technique except for kind of this formula to follow. Okay. This one's a little messy, but this is the reason why we got a product rule. Again, the last one we had to have that product rule because there was no way to multiply x squared times sine x. I mean, that's already being done, right? We had to use the product rule for that. We could FOIL this out, but that, again, it's looking like it might be something very messy, so we use the product rule. What should we do to this first part that I'm going to call f? Anybody?
We use the power rule and follow up the line, but give it a negative.
Good. Move it so everything's on. So it's going to make it easier down the road. We're going to rewrite this as y to the negative 2 minus 3y to the negative 4. Okay, because that's just going to make it easier to use. So we use that version. So sometimes we do that. The other one's okay as is. We got y plus 5y to the third. Okay, and again, we just get our pieces. We got a first piece. We've got its derivative. We got a second piece, we got its derivative. And then in the end, we're going to put first piece times the derivative, the second piece times the derivative. Okay, and again, the order's not, you'll get what feels good to you. So, again, the first one, that's what's cool is you just rewrite it, right? Y, I guess I could have just done it over here, but minus 3 y to the negative 4. And now that I'm focused on this one little piece, it's just natural to go ahead and take its derivative. And this way I don't mess things up by putting it all together and trying to do it all on one line in the way that, again, a lot of people teach it that way. But, okay, so a negative 2 comes down in front, right? And then what happens to the exponent? Subtract 1, so it becomes negative 3. Okay, so that's this. Again, negative exponents kind of threw me off as well because it feels like it's getting bigger, but no, it's getting small. It's getting more negative. Okay, negative 4 comes down, so a negative times a negative becomes a positive. 4 times 3 is 12, and then we get y to the negative 5. There we go. Okay, so you see, each step we're just doing what we did before, following the power rule. G, we just copy it over. Y plus 5y to the third. And again, sometimes I'll put that little 1 to remind myself that 1 is going to come down, 1 in front, and then I subtract 1, so that's y to the 0. So that just becomes 1. That's one of the, that derivative, oftentimes people will forget about. Or when they take it, they actually just ignore it. They don't write it down as if it were 0. But y or x, the variable by itself, when you take its derivative, it's 1. It's got to be there. Okay, so watch for that. And I'm one of those people who did that. So when I call someone out, usually it's because I did it. Okay, and then we got this 3 coming down, so 3 times 5, that's going to give us 15. We subtract 1, y to the second. Got my pieces. I just go over to the shop bench, put them in place, and I'm done. So now I need my f. Oh, that's this thing right here. Y to the minus 2, minus 3, y to the minus 4, times the derivative of g. So now make sure you're getting your right pieces. So that's this piece here, 1 plus 15 y squared. And then we have this plus, and then we've got now the g part that had nothing done to it, so the original g. So that's going to be y plus 5, y to the third. And you can color code. Sometimes that's helpful, or highlighters. And then what the last part is this one here, the derivative of f. So then it's negative 2, y to the minus 3, plus 12, y to the minus 5. Are we done? I am. We got the derivative. If we need the rate of change, we plug in a value for y, we got it. It's perfectly fine. Again, especially in this beginning part, that's good. Okay, if we need to mess with because that's going to be a mess to multiply out, right? That's why we got the product rule, so we don't have to multiply it out. Otherwise, we would have done it at the beginning. If we had to multiply it out at the end, why not do it at the beginning? It would have been easier to do and just take that derivative. So that's my... Plus, when you've got these pieces, you can kind of see where everything came from. And in mathematics, that's the thing. We look for patterns. We look, this piece came from here, that piece came from this, because these equations that we deal with are from processes. Guys are engineers, right? They are actual physical things. There's some part of the factory thing that's going on, or the production thing. That's what they are. And I need to be able to determine where they're coming from. So I leave them. Mathematicians want to, quote, simplify, but I've never seen simplification as making anything easier. It always seems to be, I think, should call it complify. I don't know. Anyway, that's the product rule. Okay. There's a few problems in the homework. You'll get practice with it. That's all you got to do. What is it? F dg plus g df. You remember that? That's all you need to know. Take the pieces, break them apart, take a derivative, put them back together, you're done. Same thing's kind of going to happen with this quotient rule. To develop the quotient rule, we're going to use a process that we've already developed, that we've already known. And so what do you see about... So this is a quotient, right? It's got a numerator and a denominator. What could we do so that we already know how to take this derivative? What could I do with that denominator? I could sort of distribute it to the numerator and make it not a fraction anymore, right? So I take x squared and I divide it into each of these. So I'm going to do that so I know what the answer is, and then we're going to introduce the quotient rule, not so that, again, this I think is probably the easier way to do this particular problem, but we're going to get ones that are quotients that are not going to easily divide into each other, so we got to have a way to directly take its derivative. So I'm going to rewrite this as x to the fourth divided by x squared is x squared, right? Negative 5x to the third divided by 2, or x squared, is going to be negative 5x. Right? And then the square root of x divided by x squared, think of that, that's x to the half, and then I divide off by x squared. I could rewrite that as x to the minus 3/2. And I was doing this at home and I just cut my error because I didn't get them to match. Now I know why. I didn't have that negative on the 3/2 because I did it in my head. Okay. So far, did I get it right this time? It looks like, okay, because I was off by a negative and now I know what, I think, I remember what I did. Okay, so now we're going to take its derivative because this is just a polynomial, right? We can go term by term. So we'll call, this is still f, it's just, quote, simplified. So this one, the 2 comes down, subtract 1, x to the first, so 2x. The second part, the 1 comes down, so we get a negative 5. Subtract 1, that's x to the 0, that's 1. This last one, the 3 halves, the negative 3 halves comes down. And then when we subtract 1, what do we get? 5 halves, right? And so just remember, thinking when we're subtracting 1, we're not 3, 2 over 2. So that's going to give us negative 5 halves. Okay, so what we've done is we just want to make sure that our answer that we get will sort of match up. Although it might not match up because we're not going to simplify what we end up with, but we could do it this way. Okay. The other way is to look at these as two separate functions. And again, we'll use f and g, so we'll call the top one f, the bottom one g. And we're going to see, because that bottom one, right, we could have just written it as x to the minus 2. We could have kind of used the product rule, and that's what I was kind of basing it by. The thing is when you use the product rule, what happens to the plus? If we bring an exponent up from the bottom, it's going to become negative, right? And when we use that power rule, when a negative exponent comes down, what's going to happen to a plus? It's going to turn to a minus. Okay? So the rule is going to be very similar. F dg, but instead of plus, we're going to get minus g df. And since what this thing really doesn't go away, we're going to get this bottom part squared. Okay, and we'll get a formal definition, and this is a harder one to try to play around with because it works though. So it's kind of like, okay, this will work. Will we get exactly the same form as that? We won't. But if we wanted to simplify it, it would eventually get there. Okay. So again, we just come off, maybe it's about time to get so much going on, we'll change some colors here. So take our pieces. Let's go with this. Little f prime, little g prime. Okay. F. Again, this part's just copying. It's the top part. X to the 4th minus 5x to the 3rd. And I'm going to rewrite this as x to the 1/2 just because it's going to make taking the derivative a little easier. And while I'm here, I'm focused on the top function. Let's take its derivative. And notice this is just what we've been doing, power rule, right? 4 comes down. 4x, subtract 1 to the 3rd. This 3 comes down, 3 times 5, 15. Subtract 1 from the exponent, 2. This one, the last one, comes down, 1/2 comes down, so it's plus 1/2. When you subtract 1 from 1/2, what do you get? Negative 1/2. So again, that's another area where some of us might forget about that negative, but there we go. So that's that derivative. And again, we're going to assemble the pieces later. G, we just write it down. This one's nice and simple. It's just x squared. And G prime, nice and simple, 2x. Okay. Put the pieces together into the formula, we'll be done. So over here, we take f. And again, it is important to make sure you got the negative. And I always get to this point. Yes. Did I get it backwards?
I think so, yeah. I think it's
High d low minus low d high. No. I think I got it right.
the textbook it says g of x and then d over d of x.
Oh. That's why. I never got that one right. That's why. Okay. Thank you. I was feeling uncomfortable, but I go, wait, no, I got it right. Okay. So, thank you. So, this part of the lecture we'll revise. So, that's why I said it is important. And that's the other part I messed up on, is okay, now I understand where all my errors are. So, we'll use the eraser. We'll erase the evidence. But see, that's the cool part about doing this, is over here I got my work. I haven't messed anything up yet. As long as I just come over here and move my primes. So it's d high. So we take the derivative of f first times g, then take the derivative of g times f. Thank you. Okay. And the denominator is going to stay the same. But now I can reassemble my pieces. Okay, so the derivative of f is this second one here. So I just rewrite that. And again, it gets long and outstretched, times g, which is x squared. Now this one, if you want, you can distribute that through. That's not so bad. Again, I'm fine with not having it distributed through, but, and then we take the derivative of g, which is 2x, and then the original f, which is this piece here. And since I'm running out of room, I'm just going to point an arrow. This whole thing goes down in there. And then we divide it by g squared, which is x squared squared. So you'll get x to the fourth. Okay. And that's one of those things, why do we have to square it? Because it works. And again, if you want to know why, clearly you can look at the book, which takes a limit approach, and there's a couple steps where that comes out. But to me, it's no more enlightening than just saying it works. It's what needs to be done. Just like FOIL. After a while, you first, outer, inner, last. It will work. Okay. We okay with that? Now that we got the correct method, now we're going to have to, let's do this. See if I can keep those so far. Oh yeah, I don't need to change this. Actually this is a picture, so I can't change that, but we'll do it. I was one of those kids that, the other students in the class would come up with these neat little ways to remember things. And again, I'm dyslexic, I turn them all around, and so I remember them backwards. So the formal quotient rule is this one, g d f of x minus f of x times the derivative of g of x, where f is the top, g is the bottom. Should have looked more closely. And so we can write it with the prime notation. Again, that's the one that I just am more comfortable with. And so that's going to be, first we take g, and then we take f, the derivative of f, subtracting f derivative of g. And that's what I was thinking when I was wrong, because it's g, the bottom, when you take its derivative, that's where that negative comes from, right? Because it was in the bottom. And then you get the bottom squared. So whatever it is, we square it. So you end up with two of them. And again, we'll have to do some work on this one. It's D high, low, and D low, high. So, but still low, low in the bottom. So I don't know, they had me memorize it. I didn't really even know what I was saying. And again, that's why I got it saying backwards. But take that derivative. Just realize that it's the negative comes from taking the derivative of the denominator. Okay. So maybe we'll just, that caused me more problem than anything. Okay, so we're going to take a couple examples. Where are we at? Okay, we got 10 minutes. So now we're actually going to be able to get all the derivatives for trig functions, because Tangent is what? It's the sine of x over the cosine of x. So we can actually derive this. We don't just have to say what it is. Well, in the end, we'll probably just try to remember it, right? So let's see if we can use this formula approach. We've got the top, which is f, and the bottom, which is g. So again, I'm going to go f prime, g prime. F is sine of x. What is the derivative of sine of x? Cosine x. Okay, so you get this practice all the time too. And then g of x is the cosine of x. It's the denominator. And what's the derivative of cosine of x? Minus sine of x. Good. And we looked at it again just from looking at the graphs. That's what it is, right? You could look at limits and stuff, but it is because it is. Now we put the pieces back together and hopefully in the right order. Which one is it? It's the derivative of f first, right? Times g minus derivative of g times f all over g squared. And again, that's why I had my little card. I had those little formulas there, and then I could get using them in the right order. So derivative of f is cosine of x. G is sine of x. Minus derivative of g, which is going to be a negative sign, so this negative becomes a positive, times the original f, which is sine x. All over cosine x. And we could, this one we put the square, cosine squared x, right? Now we might want to simplify. Did I get that right? So far it looks good. I could factor out a sine. I don't know if that'll help. Let's see. I got a sine squared.
I think the g is cosine of x. Cosine x over cosine x.
G is cosine of x.
The f prime is
The
cosine.
equation.
Yeah.
The equation, first part of the equation is cosine x.
This one here.
After the sine x, cosine x, you have another
Cosine x. Oh, it's g. Thank you. Thank you. I was going, this doesn't look like it's going to simplify to what I know it's supposed to. Thank you. So this part, yes, should also be. So not only do you need to get your pieces right, you got to put them together right. Okay, so look over that. So this is cosine x, g cosine x. Okay. It makes it much nicer. And what's so this is cosine squared right in the top, plus sine squared. And what is cosine squared plus sine squared? It's 1. So there is a trig identity that is actually going to simplify things. So this is 1 over cosine squared x. And what's another way to write 1 over cosine squared x? Secant squared x. Okay, so these are getting back to your trig identities. Get that card out, look at it, because you're going to need to be using them, and you don't want to be looking them up each time. And you don't want to be like me, trying to think that you remember something, but you remembered it backwards, and it messes you up. You did everything else right, but you got the one part that you pulled out wrong. So yes, this is going to be secant squared x. So this is one of the facts we're going to remember, that when we have tangent x and we take its derivative, we're going to get secant squared x. We're not going to do this each time. At least I wouldn't suggest it, because it's too error prone. So what we're going to do is, here's a little card, and that's in the book. So they went through and they did it with the other ones. Again, I just put it over there and just try to remember these are the derivatives. Okay, it'll make it easier to go through. We okay with that? Okay. Now this one, I wanted to get a look at this one. This will probably be our last one we look at. But what do you notice in that numerator? It's what? Right, we can do tangent, it's going to be, we can just make it secant squared, but what else do you see next to the tangent? An x squared. We've actually got to use a product rule in the numerator to take its derivative. So this is not just this is a combined, we're using the product rule within the quotient rule. Okay, so it's where we start to get a little bit of practice. So what we do, yeah, you could always do that, yes. Sure, yes, there are multiple ways to do it. So yeah, if you've got your trig identities, you can maybe simplify it. Oh, that's going to be easier to work with, just like we could do with algebra, certainly. But I'm going to try to show you, because sometimes, yeah, we've got to do a product rule inside of a quotient rule. That's why I chose this one. And as you can kind of see, it's got the gray background, which means it came from the homework. Okay, so I wanted to help you get your way. Okay, so we're going to take the first function, the top function is 2x squared, tangent x. Let's take its derivative while we're here. Now when we take, this is where we kind of are going to get to. If you wanted to, you could break it into two pieces and go overdo it. But I'm going to try to do this on the run. So the first part is 2x squared, right? So what's the derivative of 2x squared? 4x to the first. So I took the derivative of just that first part. I'm going to keep the tangent x, because that doesn't change. And notice right now I'm doing a product rule on that first part. And then now I'm going to take the first part unchanged, and again, order doesn't really matter, and then I take the derivative of tangent x, which is secant squared, which we did last time. We don't have to redo it all. That's why we don't want to redo it all. It's just going to be this. Okay? So it's kind of like, eventually you get to this place, but it might be a little bit early. If you're just doing the product rule, you break it into its pieces, but eventually you stop breaking into pieces and you start doing it mentally, just because it's easier. G of x is okay. It's just going to be secant squared, or secant of x. And then we're going to take its derivative. I'm going to cheat a little bit because I don't remember what it is. Secant is actually secant x tangent x, because I don't want to do it. I don't want to make it up. So I just use this fact. Derivative of secant is in turn secant x tangent x. Okay? So that's when I go to trigs, that's what I'm just going to take it, remember it. Now I put my pieces together, right? Hopefully the right way. So it's derivative of f times g minus derivative of g times f all over g squared. Derivative of f. Okay, so notice I get this whole thing right here. Again, and sometimes, you can simplify or not. And again, today, what I'm looking for is just that you get these product rule, quotient rule thing down. Algebra is going to get a little messy. And then times g of x here, the secant x. But you're already getting good because you're catching all my errors, which is, right? Derivative of g, which is this one up here. Multiplied by the original f, which is 2x squared tangent of x. Divided by secant squared x. And again, it might be beneficial if you want to go through and do a little bit of algebra. It probably will simplify down to get some things canceling. But it's also, that's a derivative, right? What is a derivative? Whoa. Say it in your sleep. Rivet of the slope. The rate of change. And then we get to it. Good? What's that? Yeah, so we'll get there. We'll learn a lot of techniques, and then it's going to be what's the easiest way to do this stuff. A lot of times it's easier to algebra the first Well, look at the book. It should have.
There's so many spoilers. I've seen like everywhere on the internet. It's just I'm like, bro, if I never caught up before all this stuff, you know, how would it go?
Yes, those get updated.
I did every question right. And Sean, like in this question, like the virtual, you could do like project to sign it for the cancel, we could do anything.
Anything you want. There's more creative things. Awesome. Okay, good. I got someone else doing a makeup test on Monday. How do you feel as far as preparation? I don't want to rush you into it. If you can, that would be fine. If you feel like you want a little bit more time to review because you've just got access to the campus now. Okay. And you do have access to the canvas. Like I said, just pull. I got a review exam in there. Take a look at that, and then after class, you can just follow me. Go to my office. Sit you out. Welcome to class. Okay. Whoa, everyone cleared out pretty quick. Must be the weekend. What's your name?
My name is Ariel.
Ariel. And what's your major?